Good morning, dear students. My name is Ferhan Mazher, and the subject today we are studying is Cambridge O Levels Physics 5054. Today we have set our heart to solve a paper 4 of this subject. We call this paper ATP paper, and today we have selected October-November 2024 4-2 paper. This paper and the marking scheme of this paper, they both are the properties of the Cambridge Assessment International Education. They have created this paper. I have just downloaded this paper from their website and I'm using this paper. The paper and the marking scheme both are the properties of the Cambridge Assessment International Education. I am just presenting you the solution of this paper to the best of my knowledge, to the best of my abilities in this video. So let's start today's paper. So this is paper 4 and alternative to practical. The time allowed for this paper is 1 hour, and the numbers, the total marks for this paper, they are 40. So the first question is showing up on your screen. A student determines an approximate value for the density of the glass from which a test tube is made. The height h and the external diameter d of the test tube are shown in the full size diagram of the tube. So here you can see a test tube is shown and its dimensions, its height and the external diameter, they are given. The external height and the external diameter is given. This diagram is full size. So by measuring the h directly with the help of a scale, you can tell what is the external height. And by directly measuring with the help of the scale, the d, the external diameter of this test tube can be calculated. Their question is, so the question they are asking you is to measure. Measure means to use the scale. Measure the height h of the test tube in the figure 1.1 to nearest 0.1 centimeter. And the second part is measure the external diameter d of the test tube in the figure 1.1, the small d. Okay, so use a scale and measure what is the d value and what is the h value. We have done this calculation. We have done this measurement, and because whenever we photocopy a paper, and the figures, they shrink a little bit, so our answers will be a little less than the actual answers. So when I measured h, it was 14.4, and when we measured d, it was 1.5. Okay, so our answer is 14.4 and this says 15. So the D is 1.5, so there's no problem. Just don't worry about this. Okay, now the next part. The B part of the question number 1. The student uses a ruler and 2 wooden blocks to help obtain an accurate answer for the height. Figure 1.2 shows how the student uses these wooden blocks. So he has placed the test tube between the 2 wooden blocks you can see in the diagram. And if you measure the distance between the 2 wooden blocks, that will be the external height or the length of the. Explain why it is important for the student to ensure that the blocks are parallel to one another. If the blocks are not parallel to one another, then depending upon that from which side you are measuring the height will be either more than the real height of the test tube, or it will be less than the real height. So it is very important to make sure that the blocks are parallel to each other. If they are not, then you will not be able to find out the real height. You see here we have tried to explain to you, if the blocks are not parallel to each other, they are like making some angle with each other. Then if you measure that height of the test tube from here, it will be less than the real height, and if you measure from here, the height which you will get will be more than the real height. So explain why. If the blocks are not parallel, distance between the blocks is not constant. So it depends upon if you are measuring from here, or you measuring from here, or you measuring from here. The distance between the blocks will be different. Okay, so you will not be able to accurately measure the h value. Okay, so question number one and its C part. He says the shape of the test tube is approximately a cylinder. So calculate the external volume VE of the test tube using the equation. The external volume is equal to 0.79 D square into H. The value of the D and the H we have in the A part. So from there, I will take those values and I will put them and I will just calculate this answer. So here you can see, so 0.79 multiply 1.5 whole square into the 14.4. Our answer is 14.4 of the height, and the marking scheme says it should be 15. You can use 15 or you can use 14.4 in the when you will be actually using the Cambridge exam paper. There the heights will be perfect, and the difference is because of the photocopy. So just put these values, multiply them, you will get 25.596, so approximately 26. So the volume is 26. They say the volume will be 26.66. Our answer is right. Okay, so D part. The student, question number one is D part. The student fills the test tube to the top with water, pours the water from the test tube into a measuring cylinder. And figure 1.3 shows the measuring cylinder. So what they have done, they have filled the test tube whose volume they just calculated, and they fill it with the water. Then that they poured that water in the test tube into a measuring cylinder, and from the measuring cylinder they are going to measure that what is the volume. So the volume right now I can see, I can tell you the figure 1.3 shows the measuring cylinder. Record the reading V1 on the measuring cylinder. This is the internal volume of the test tube. So that the internal volume will be approximately how much? It is 21. Let me show you. I hope you can see that. This is 20, this is 19, this is 21. So the reading is basically 21. Okay. So I will write here 21. 21 centimeter cube. Yes. Okay, then they say E part, question number one is E part. It says calculate the volume Vg of the glass in the test tube using the equation. The volume of the glass is equal to the external volume minus the internal volume. So we know the external volume, we know the internal volume. We will simply subtract them. 26 minus 21. So that is 5. So we think that the volume of the glass is 5. Okay. You see, our answer is a little different because of the height. Okay. He says suggest one source of inaccuracy in measuring the internal volume of the test tube. Uh, when we are finding the internal volume of the test tube, we are using water. It's possible that the test tube is not completely filled. It is possible that some of the water is left with the walls of the test tube. It is also possible that when you are pouring the water from the test tube into the measuring cylinder, maybe some water splashes and fall on the table. So these are the some reasons. Some water is left in the test tube, some might spill while pouring. Okay. So you can have a look at the marking scheme here. Question number one is G part. He says the student uses a balance to measure the mass M of the test tube. Figure 1.4 shows the reading on the balance, so it is 0.01375 kg. Record the M to the nearest gram. So you will multiply this reading with the 1000, it will be converted into the gram. So it will be 0.0, when you multiply with 1000, it will be 0.01375 gram. So to the nearest gram, When you multiply it with 1000, it will become 13.75 kg. It's already 0.01375 kg. You multiply with the 1000. So this will become 13.75 grams. So when you want to convert this in, I mean, if you want to represent it to the nearest gram, so it will be 14 gram basically. 14 gram is the answer, sir. The answer is right. You can see here. Okay, then the second part is use your results from the G first part and the E to calculate the density rho of the glass from which the test tube is made using the equation. Density, which is represented with the rho, density is equals to mass divided by the volume of the glass. Give the unit for your answer. Okay, so if I will use the mass in grams, that's 14 gram, and and we know the volume of the glass, so 14 divided by 5, and that will be 2.8 grams per centimeter cube will be the unit. 2.8 grams per centimeter cube will be the unit. So our answer is right, sir. This is the G part. So that was question number 1. So we are going to the next question. The next question of this paper coming up on your screen is question number 2. He says a student investigates the resistance of a light emitting diode when different currents flow through it. The student sets up the circuit shown in the figure. So here you can see we have a power supply. Here we have a switch. Here we have a fixed resistor whose resistance is 270 ohm. And here we have light emitting diode. Okay. He says the student connects a voltmeter across the 270 ohm resistor between the point X and Y, closes the switch, records the voltmeter reading of the potential difference in the top row of the table 2.1, and opens the switch. So they have connected different resistors like fixed resistor 270, 470, 560, and they have noted down what is the voltage across the resistor and what is the voltage across the YZ, means about the diode, and then you have to add both the voltages. You have to how much is the current flowing. We have connected an ammeter here. No, we have not connected an ammeter here. So, and then you have to calculate what is the resistance of the LED. Okay. So on the figure 2.1, draw the symbol for the voltmeter connected to measure the potential difference Vx across the 270 ohm resistor. So if you want to find out the voltage drop across this, so you have to connect a voltmeter here, which is parallel to the XY. So here you can see on the diagram that we have drawn a voltmeter which is parallel to the fixed resistor, and it will be able to tell you the voltage drop across the fixed resistor XY, voltage VXY. Okay. So then the question is, okay, let me go to the question. This is done. Figure 2.2 shows the voltmeter reading of the potential difference Vxy when the voltmeter is connected across the 270 ohm resistor. Record the Vxy. So what is this reading? 1 volt, 2 volt, this is 3 volt, this is 2.5 volt. So in that table where you have Vxy, you will write 2.5 volt. This is the question, 2.5 volt. Okay. Then they say the student disconnects the voltmeter from the point X and Y, reconnects the voltmeter across the LED between the point Y and Z, closes the switch, records the voltmeter reading of the potential difference V YZ in the correct row of the table 2.1, opens the switch. Calculate the value of the, you have to add up VXY and VYZ for the 270 ohm resistor, record your answer in the table 2.1. So in that table, we have to put the recording, our reading. Okay. So this is 2.5 volt. This is 2.1 volt. We just add them up. That will be the total voltage. So from here, just ask us to do this. In the second part, it says the current I in the circuit can be calculated using the equation I is equals to V across the XY divided by the resistance, that is 270. So VXY, we know that is 2.5, and we will put that value. So 2.5 divided by 270 is equals to 9.259 x power minus 3. So that is the current which you have to feed here in this table. So that will be, when you write it in the normal form, it will be 0.0093 ampere. Then the question is the resistance of the LED, or the LED can be calculated using the equation, the voltage across the XY divided by the current through that circuit. So we know that current, so the voltage across the YZ is 2.1 volt, and the current flowing through, because both the fixed resistor and the LED, they are connected in series with each other. So both of them have the same amount of the current in them. So 2.1 divided by the 0.0093 ampere. So you simply divide them and you will get the answer. And we have noted down that answer here. So the answer will be 230 ohm. 230 ohm. LED resistance will be 230 ohm. So the student repeats the procedure in the A and the B, replacing the 270 ohm resistor first with a 470 ohm resistor and then with the 560 ohm resistor. The student's results are shown in the table 2.1, but the value of the VXY for the 560 ohm resistor is missing. Calculate the VXY and record your answer in the table 2.1 on the page number 3. You see, we know the total voltage drop and we know the voltage across the YZ. So from this total, I will subtract this 4.6 minus 2.0, you will get 2.6. So now you can see this table is complete. Okay, then he says, as the resistance between the terminals X and Y changes, the current in the circuit changes. Examine the results in the table 2.1. Describe how the change in the current affects this. Okay, so if you look at that table, the current is basically decreasing. So when the current is basically decreasing, the total voltage drop is not changing. Okay, the total voltage drop is not changing. Their question is the effect on the total voltage drop. So that is not affected. So let me find the answer written here. So from the table, I can show you that as the current is being changed, the value of the Vxy plus the Vyz, the total voltage drop is not changing. You know, the total voltage drop is always equal to the voltage of the battery. So because the voltage of the battery is whatever it is, so that is not affected, though there is no effect. Okay, so let me check the answer. That remains constant. Okay, then their question is, when the current is changing, what is the effect on the resistance of the LED? Okay, what is the effect of this thing on the LED? Look at the table. we have to look at this table. So as you see, the current is decreasing, the resistance of the LED is increasing. Yes, the resistance of the LED is increasing. From that table, I can tell you this. As the current decreases, the resistance of the LED increases. This is from that table I can tell you. Okay. Then the question is, another student assembles a circuit using the circuit diagram shown in the figure 2.1. This student finds that when the switch is closed, the LED does not light up. The student tests the components and find that the power source is producing the EMF and that none of the other components are broken. Suggest the error this student has made while assembling the circuit. You see, the reason can be because the diode, it only let the current flow through it only in the one direction. If the direction of the conventional current is along with the arrow of that diode, it will let the current flow through it. We say this is forward biased. And if the conventional current is opposite to the arrow of the diode, then what happens? It do not let the current flow through it. Maybe everything is good, and your diode has been in the reverse bias. The LED is connected in the opposite direction to the conventional current. So, or you can say the diode has been connected in the backward biased. So he has many reasons. He says the diode connected the wrong way around, the battery connected the wrong way around, and the voltmeter connected in series. If you connect the voltmeter in series, even then this can happen. The resistance of the whole circuit will become higher and the current will not flow through it. So, most probably the LED is in such a way that it is in the backward biased. Okay. So then we have, he says, name and draw. This is the F part. He says name, name, and then he says draw the symbol of a single device that can be used to change the current in the circuit without the need to connect different resistors across the terminals X and Y in the circuit in the figure 2.1, name of device, symbol of the device. So you can use, variable resistor. And by just changing the resistance of the variable resistor, you will be able to change the current in the circuit. Or you can use a variable power supply, and by changing the power, the voltage of the variable power supply, you can change the current flowing through the circuit. So we have chosen that the variable resistor, you can connect their variable resistors. By changing the resistance of the variable resistor, you will be able to change the amount of the current flowing through the circuit. So symbol of the variable resistor is this. You draw a rectangle, and through that rectangle, you pass an arrow. It says variable resistor and the correct symbol used. So that was your question number 2. Okay. Hopefully you understand this. Now we are going to the next question, and that is the question number 3. He says a student investigates the image formed by a converging lens. The student arranges the apparatus as shown in the figure. So here we have the light rays, rays of the light from a distant object such as a window. Here you have a lens holder, and in that lens holder we have a convex lens, and the light rays which are from a distant object passes through this lens, and they are converged here. This is a screen, and this whole thing is on a bench. On the screen, a sharp image of that window is formed. That image is real, so that will be inverted on the screen. The image will be inverted on the screen. He says Place a white screen approximately 30 centimeters from the lens. Adjust the position of the screen until a sharp image of a window in the laboratory a few meters distant from the lens is formed on the screen. Measure and record in centimeter to the nearest 0 0.1 centimeter. The distance acts on the figure 3.1 from the lens to the screen. So we can find out this distance between the lens and the screen, which is called x. And he says just measure it. So we can measure it with the help of a scale, and we have measured it. So let me show you. So we have measured that distance, and that is 4.9. And let me check here. It will be a little less than the real answer. Our answer will be always a little less than the real answer because when you photocopy, the diagrams shrink a little bit. So our answer is 4.9 centimeter. Marking scheme says it will be 5.1 centimeter. So our answer is right. No, there's no problem. Okay. So then their question is the distance x shown in the figure 3.1 is drawn to a scale of 1/3 full size. It means if something is 1 centimeter, in reality it is 3 centimeter. So use your answer from the A first part to calculate the actual distance from the lens to the screen. The distance is the focal length L of the lens. So whatever is the reading, we have noted down that is 4.9 because the actual length will be 3 times more. So 4.9 multiplied 3, that is 14.5. So the 14.7, sorry. So they say the reading will be plus minus. This is which part? This is it is F. This is the question number 3A and its second part. Question number 3A, second part 15.3. Our answer is 14.7 because this reading is a little bit less than the real value. But our answer is right. The technique is same. Okay. The student rearranges the apparatus as shown in the figure 3.2, illuminated triangular object. So here what you have a bulb. In front of that bulb you have placed a cardboard, and in that cardboard there is a small gap. So from this gap the light rays will come out, and this will act like an object for this lens. So here we have a lens, and the distance between the lens and the object is u. And here we have a screen. You will move the screen forward backward, let's say, and whenever you get a sharp image, or you can move the lens also, and whenever you get a sharp image you place the screen there, and at that time the distance between the screen and the lens is v. He says switch on the lamp places the lens a distance u of 20 centimeter from an illuminated triangular object. So this u is constant. It is kept on 20 centimeter. So to get a sharp and clear image, I will just move the screen. Adjust the position of the screen until a sharp image of the triangular object is formed on the screen. Measure the image distance v from the lens to the screen, and the v here is 60.5 centimeter. Calculate the value of the u plus v. So it will be 20 plus 60.5, so that will be 80.5 centimeter. Then he says, record your values of the u plus v and the uv to an appropriate number of significant figures on the answer lines and in the first row of the table 3.1. So you just add them, 20 plus 60, that will be 60.5, that will be something like 80.5. So when you round it off, it can be 81 centimeter. And you multiply the 60 with the 60.5, and that gets 1210. So let's check. So our answers are approximately right. Okay, then they say the student repeats for values of the u between u is 25 centimeter. U is the distance between the object and the lens. So he changes that distance from 20 to 25. and do that calculation, and then he made the U 55 centimeter. The students' results are shown in the table and add appropriate units to the headers of the last two columns. So U plus V will be in the centimeters and U multiply V will be centimeter square. So here we just calculated this answer, that was 80.5, or you can round it off to 81. And we multiply this, that is 1210. So we will put these values in this table. So here you can see that we have filled that table. So here I have written 81 and here we have written 1210. Okay, so we are going to use this. Okay, then their question is, oh my God. On the grid provided in the figure 3.3, plot a graph of the UV on the y-axis against the U plus V on the x-axis. You do not need to start either axis from the origin. Draw the straight line of the best fit. So here we have a graph. So here on the y-axis, you will have UV. On the x-axis, you will have U plus V. And this is the table. So UV is 1, 12, 10, 933, 988, 1090, 1140. So it's starting from approximately 900, and the U plus V is starting from the 60. So we can also start our graph from these values. So you can see on the x-axis, we have started from the 60, then we have 70, then we have 80, then we have 90. On the y-axis, we have started from 900, then here we have 1000, 1100, and here we have 1200, and here we have 1300. So what I will do, I will plot those points from that table. So I plotted this point, this point, and this point, and this point, and this point. And then I have drawn the line of the best fit. The line of the best fit is such a line which is joining all those points. The maximum number of points should be joined. The line should be in the same pattern as those points are making a pattern. And the line should be passing in such a way that the number of the points which are left above that line are equal to the number of the dots left below that line. So this is the line of the best fit. I hope you can see it. Okay. Then their question is, calculate the gradient of the line, indicate. Then their question is, calculate the gradient of this line, and then they want me to indicate on the graph the points you use, show all your working. It's a 2 marks question. So I am going to use, I will take 2 points on this graph. So we have taken this point is 65, 985, and we are going to use this point which is 975, and it is something like 1125. Okay. So then I will, on the graph, I will show this triangle. I will join these 2 points with the rectangular components. And I will use the formula, the rise divided by run. So the gradient is y2 minus y1 divided by the x2 minus x1. So this gives me the gradient. So 1125 minus 985 and the whole thing divided by the 75 minus 65. So the answer will be 14. He says that the answer will be 15 plus minus 3. So our answer is in this range. So our answer is correct. Hopefully you understand that we have used these 2 points and we have done this calculation for the gradient. Okay, so the next thing is that the 2 quantities, they are saying that the 2 quantities can be considered to be the same within the limit of approximate experimental accuracy if their values are within the 10% of each other. The gradient of your line calculated in the E part is numerically equal to the focal length f of the lens in the centimeters. Compare your values of the f obtained in the A second part with the values of the gradient obtained in the E part. State if your two values can be considered to be the same. Support your statement with a calculation, and it's a statement with the calculation. Okay. So the value we just calculated is 14, and the value in the A second part is 14.7. So the difference between them is 14.7 minus 14 is 0.7. So the difference divided by the original value multiply 100, so that is 5%. So the answer which we just calculated is 5%. The difference is just 5%. So they can be considered the same as they are within the 5% of each other. Okay. So next thing they are asking us to do is G part, question number 3. And when measuring the object and the image distances from a meter rule, it is important to avoid the line of sight or the parallax error. State how the student avoid the parallax error when doing the experiment. You see, the line of sight must be perpendicular to the scale. The line of sight must be perpendicular to the scale. By keeping the line of sight perpendicular to the scale, reading. Okay. Then they say, describe a technique that the student uses to make sure that the image on the screen is as sharp, focused as possible. You do the hit and trial, you move the screen forward, backward, until you get a position where the image formed on the screen is very sharp. And so move the screen forward and backward slowly until you get a point where the image is sharp on the screen. So move the screen slowly backwards and forwards until the image is as sharp as possible. So this is how you do the question number 3. So here we have the question number 4. This question is basically about the planning. This is a planning question. So we will learn how to plan an experiment. So, my dear students, this is question number 4, a planning question. Water is heated from room temperature to its boiling temperature in a glass beaker. Plan an experiment to investigate if the time taken for the water to reach its boiling temperature depends on the diameter of the water surface exposed to the air. So, very simple. What you can do, you can take a beaker of smaller size, and you can put the certain volume of water in it, and you can note down its initial temperature, and then you can start heating it and note down how much time it takes to reach to the 100 degrees centigrade temperature. Then pour the same amount of the water in a little larger beaker and note down its initial temperature. The initial temperature, the room temperature should be kept the same. The material of the beaker should be kept the same. The amount of the heat, the stove which you are using or the Bunsen burner you are using should be the same. And you should note down how much time it takes from that room temperature to go to the boiling point. And then use another beaker with a larger diameter, even larger diameter, and do the same process. So every time you have to measure what is the diameter of the beaker, and you have to note down what is the how much is the volume. Every time the volume of the water should be same. The initial temperature of the water should be kept the same, and the room temperature should be kept the same. The amount of heat you are providing should be same. The only thing should be changing is the diameter of those beakers in which you have kept the in which you are boiling the water. So he says plan an experiment to investigate if the time taken for that water to reach its boiling temperature depends on the diameter of the water surface exposed to the air. You are provided with a supply of the cold water, a set of glass beakers of different sizes, a Bunsen burner, tripod, and a gauze. A measuring cylinder. You may use any other common laboratory apparatus. In your plan include include any other appropriate apparatus needed, a brief description of the method, including what you will measure and how you will make sure your measurements are accurate, the variables you will control, the results tables to record your measurements. You are not required to enter any readings in the table, how you will process your results to draw a conclusion. You may include a labeled diagram if you wish. And this question, my dear student, is of how many marks? This question is of 6 marks. So basically, they are asking you to investigate the time taken. Let me reduce the size so you can see the whole question together. So now you can see the whole question together. So let's see what okay, so here we have take two wooden blocks and place the beakers between them, and you will be able to, with the help of a scale, you will be able to tell out what is the diameter of the beaker. So in this table, I'm going to note down the diameter of the beakers and the time taken for the water to reach the boiling point. So we are going to use a stopwatch, and this is how we have a tripod stand. On that we will place a gauze. On that we will put that beaker. This is the Bunsen burner. We will use a retort stand, and with the help of a clamp, we will hold a thermometer, whose bulb is inside that water to note down the temperature. We are going to use the measuring cylinder to measure the water every time we will pour that. Then we can draw a graph, and on that graph, we will use the diameter of the beaker on the x-axis. That is the independent variable, and the time taken for the water to reach its boiling point will be on the y-axis. Then we will draw a graph between them, and by looking at the shape of the graph, we will be able to tell what is the relationship between the diameter of the beaker and the time taken to boil the water. So measure the diameter of the glass beakers using the wooden blocks and ruler as shown in the figure 1. Set up the apparatus as shown in the figure 2 using the thermometer and water in the beaker, tripod, Bunsen burner, measure volume of the water using measuring cylinder, measure the time taken for the water uh, to reach its boiling point using stopwatch. Repeat this with beakers with different diameters, but keep flame initially high, distance, volume of the water, initial temperature, and room temperature constant. The bulb of the thermometer should not touch the base of the beaker. Draw a table as shown in the figure 3. Plot a graph of time taken against the diameter of the beaker, and using the shape of the graph, determine the relationship between them. So this is how you will plan a question, an experiment to investigate. So let me show you. So here, what the marking scheme says. It says stopwatch and ruler and the measuring tape. Method is to measure, record, note the diameter of the beaker, and heat and measure the time to bring the water to the boiling point, and repeat for the other beakers. Control variables are anyone from the mass, volume, amount of the cold water, same initial or cold water temperature. Keep Bunsen burner flame constant. Table columns of the diameter d and time with the units for both. Okay. And processing and conclusion, plot a graph of the diameter against the time or compare the results in the table to see if how the diameter of the beaker affects the time taken to boil the water. This is your marking scheme, and this is what my student has written. And these are the diagrams which she has shown. The units are also written here. So this is the planning question. That was the question number 4, and we have reached the end of this paper. So my dear students, in this video, we have presented you the solution of this paper to the best of our knowledge and to the best of our abilities. And remember one thing, that this paper is the property of the Cambridge Assessment International Education, the paper and the marking scheme both. I have just downloaded them from their website. These papers are not created by me. I have just written the solution of these papers. In this video, we have presented you only the solution of these papers to the best of our knowledge, the abilities. So my dear students, if you find this video useful and interesting, and you think that this video can be useful for your senior students, for your junior students, or for your teachers, please share the link of this video with them. Share the link of this video on your WhatsApp groups, in your Instagram, on your Twitter, on your TikTok, on your Facebook, on your LinkedIn, wherever, whatever the social media you are using. Please share the link of this video. The main purpose of this video is to help the students around the globe who cannot have a face-to-face teacher. So this video can help them to prepare for the Cambridge O-Levels physics exams. Thank you very much for watching my video. It's a great blessing for me that I can make these videos and reach so many students around the globe. Once again, thank you very much. Have a good day.